Hello, I'm Dr. Steven Steiner, and we're here in the Union College Aerogel Lab, known for its unique high-pressure press aerogel drying technology. We're here with Professors Mary Carroll and Ann Anderson, who's going to show us about their process and their company, SunThru, LLC.
All right. It's great to have you here at the Union College Aerogel Lab, Stevie.
Thanks.
And as you mentioned, this is a joint lab that Ann Anderson and I co-direct. And all of the students we have working in the lab are undergraduate students. Once in a while we have somebody that's a post-baccalaureate student who's we're paying off of a grant for a short period of time. But we don't have any graduate students.
How many undergrads have gone through this lab?
About 110
Wow.
since the 2001-2002 academic year.
Awesome.
You know, we have very strong students here, but they are undergraduates, so we have them in the group for perhaps a summer or a summer and a year, occasionally 2.5 years, but for the most part we're dealing with students doing short-term projects, and we design those so that they, you know, further the lab's overall research goals.
And that's something that's really amazing to me, being able to sync up all of those undergraduate projects, summer projects, senior projects over the years to actually make steady progress, and you've done an incredible job here.
Well, thank you very much. It's a lot of fun. One of the really neat things about it is an interdisciplinary research lab, so I'm in the chemistry department here at Union, and Ann is in mechanical engineering, and we mostly have students in chemistry and mechanical engineering, but we've had other engineering students, biochemistry majors, you know, so some environmental science students. So for the most part it's chemistry and mechanical engineering, but it's really nice to be working on the intersection of different fields, and I think that's one of the things that aerogels is really good for. The really remarkable properties of the materials mean that there are all of these different kinds of interesting projects to work on. So we've worked on fluorescence sensors, and we're currently doing a lot of work in catalysis, and of course the main thing that we do that's different is that we developed our own way of making aerogel materials using the hydraulic hot press. And so the students that are behind us here are working on mixing up some chemicals that we're going to use to make silica aerogels, which are essentially very low density glass. And so we're using a recipe that uses tetramethyl orthosilicate and some water and methanol as solvents, and we're just doing a base catalyzed reaction with ammonia. And so the students are mixing up the liquid precursors, and then we're going to subsequently pour them into a mold held in the hydraulic hot press, which we're going to use to heat and apply pressure on the mold. And what will happen is gelation will occur, and then we will take the liquid in the pores of the gels up above the supercritical point by using the hydraulic hot press.
Very cool. And so when you're making these silica aerogels, do you use any kinds of special formulations, or do you just use kind of standard silica aerogel?
Yeah, and that's a good question. I'm an analytical chemist by training. I'm not a synthetic chemist. And so what we have typically done when we've worked with any type of aerogels, including the silica aerogels, is we start with the literature. And we use recipes that other groups have used in the literature. We adapt them for our method. So that may be, in this particular case, playing around a little bit with how much water to methanol ratio and how much catalyst we need to get it to gel in a relatively short period of time, but not gel between when we mix it up and when we're trying to get it in the hot press.
Yeah, and that's actually a really important thing, that process optimization, right. Not just thinking about the gel result, but thinking about the humans and machines that need to actually turn that into something.
That's right. So too fast a gelation time doesn't make any sense in terms of getting it into the hot press. Too slow a gelation time means that we have a longer process than we need to in terms of equipment time. So one of the advantages of our rapid supercritical extraction method is that it's rapid. You know, we can typically make silica aerogels in sort of 3 to 8 hours. We routinely
And that's from liquid to aerogel.
That's from mixing the liquids together to aerogel. So if we're talking about if we were on a cooking show, we would talk about prep time and then the cooking time. We're talking total time. The prep time on the silica aerogels is on the order of 10 to 20 minutes, depending on how many different things we're mixing together to put in, and you know, some stirring time to make sure that the mixture is fully mixed and monophasic before it goes in, and then most of the time is processing time.
Cool.
And again, typically 5 to 6 hours, but we've done it as little as 3 hours.
And I understand one of the big things you're interested in here is making transparent silica aerogel windows.
That's right. So our process allows us to make monolithic aerogels relatively quickly. And if you wanted to do windows and you were trying to do it by some more conventional methods using critical point dryers, you have to get to very big critical point dryers, and you also have to spend a lot of time in solvent exchange.
Right.
And our method does not involve solvent exchange. It's a direct method, and so there's a big advantage in terms of scaling up. And we're able to make monolithic materials, so single piece materials, and we're using a method that's inherently scalable. We're using a laboratory scale hot presses, which we'll be showing you here, but there are industrial hot presses that are simply enormous, and so this process can potentially be scaled up to window-sized pieces of monolithic silica aerogel with very good optical transmittance.
Whereas supercritical dryers are not typically bigger than a few feet in diameter on the industrial scale, and the wall thickness scales unfavorably with diameter of the inside of the autoclave. So this is a really fascinating alternative approach to making aerogels.
And the interesting thing, of course, is the reason that we developed this method is that we didn't have a critical point dryer. So when we started to collaborate on aerogel materials, I was already working with sol gel materials for sol gel sensors, and Anne had a student come to her with one of those pictures that you see of aerogels. You've got the aerogel, you've got a torch under it, and there's a flower or a Hershey's Kiss or crayons or something above it. And it's a student that had worked with her on another project, and he said, for my senior project, I want to make one of these. And Anne said, well, then we're going to have to talk to the chemists. Sent him down to me, and I said, well, sure, I know what aerogels are, but we don't have the equipment to make them. And working over the next year, and I guess 2 years, with undergraduate students, we developed a method for making aerogels with equipment we had available, using the literature on rapid supercritical extraction methods and the fact that our mechanical engineering department had a hydraulic hot press.
Very cool. And so these are the methods that came out of Lawrence Livermore originally.
That's right.
And you've adapted them using other equipment to make a better process.
So it's just a different rapid supercritical extraction process, but it is not by any means the only one. And what we're hearing right now is the sonicator.
Let's take a look.
In the hood. So they've mixed together the various precursor chemicals, and it doesn't look like all that much. It's a clear, colorless liquid.
Sure.
And because the TMOS and the water are not fully miscible, we need to mix in some way. We're using a small ultrasonic cleaner.
This is kind of like they used to clean jewelry.
This is exactly what would be used to clean jewelry. And you can see, so it's just a very small vessel. We've got a beaker with the precursors that the students have just mixed up, and we're going to let this go for 5, maybe 10 minutes to make sure that we have a single phase, at which point we'll pour it into the mold in the hydraulic hot press.
Very cool.
So this part of the process is definitely chemistry, and Anne's going to take you through the part of the process where we're looking at the actual equipment that we're using, the hydraulic hot press.
All right.
So it's been kind of fun. We have chemistry-like things, we have engineering-like things, and we have had students that are both chemistry and engineering students.
Well, let's take a look at the engineering side.
All right.
So Anne, thanks for having me. I understand you're the engineering side of the lab.
Yes, yep. This is a really interesting lab group we have here. It's interdisciplinary mechanical engineering and chemistry. My background is actually in heat transfer, and when I had a student who came to me and wanted to make an aerogel, we went to Mary to try to figure out how to do it. And it's really been an interesting journey. It's been about 13 years when we first figured out a new way for making aerogels, which is this whole hot press method that we have here. Came about because we didn't have a critical point dryer. But we did have a hot press, came up with this new method, and since then have spent years doing all sorts of interesting things. What's really nice about our method is because we can make aerogels in 6 hours, people get really excited about that. Critical point dryer is a little more finicky, and when we're working with undergraduates who have a shorter time frame to work with us, this really works out well.
So where did you get the idea of using a hydraulic press? I mean, that's a pretty bold departure from a critical point dryer.
Well, when we were researching the literature and looking at the rapid supercritical extraction method out at Lawrence Livermore, a student actually talked to Larry Hrubish on the phone about how he could do this.
He's a great guy. I've talked to him on the phone. He
Yeah.
helped me when I was in high school,
Very
too.
helpful, very helpful. And we talked about the method they did and how they contain the mold, and we happened to have a hydraulic hot press and thought about the idea of using that to actually contain the mold and provide that restraining force.
So how do you deal with the fact that you've got a potentially flammable liquid like methanol in the pores of the gel, and it's really hot press and having to seal all of that, how do you manage that without having an explosion hazard?
Right. So there's a small amount of methanol. It's not as if we have an autoclave size pressure vessel full of methanol. What we do is you can see there's a safety shield on the hot press and a little bit of a flow up. And so when we release, we capture that gas. Now, scaling up, that's going to be a bigger issue. But for the small sizes we have never had a problem with that.
That's fantastic.
Yeah.
So can you tell me a little bit about how this machine works and turns sols into aerogels?
So it's basically just it's a hydraulic hot press. We use compressed air. We've got a pump that pumps up. There's a cylinder down below full of oil. And we pump that up. We apply pressure to one side. And the pressure in the cylinder is pushing on these platens. It pushes them together. So that provides the force. These are commonly used for laminating things where you want to either heat and then you want to squeeze something down, apply a high force. It's programmable, which is great because we start it up and then we leave and come back 6 hours later and we've got our aerogel.
Set it and forget it.
Set it and forget it. Yep.
And so the pressure inside here is generated with, you said hydraulics, so you have a pump that...
Yep, there's a pump down below here is all of the hydraulic system is set up. So there are pumps. When you start it, you can hear the pump going. Every once in a while, you'll hear the pump kick in. If the pressure is if there's not a perfect seal, you'll get a little bit leaking at times.
So what are your goals for this technology? Where would you like to see it go?
Number one, I'd like to see more people use this technology. We've been approached by people every once in a while they have a hot press, they want to try it. We'd love to see more people use it. Hope they'll see how easy it is to do. We'd also love to be able to scale this up. It's inherently scalable. We're working with a company now that has a 300,000 pound hot press. This is a 60,000 pound hot press.
Wow.
So that's the maximum force we can do, but if you want to make something bigger, you've got to go to a larger press.
So with a press like that, how big could you make an aerogel monolith?
Yeah, so what you need in the restraining force is basically the area times the pressure you want inside your mold.
Okay.
And so we need to get above about 2,000 psi.
Okay.
To go supercritical. 1,300 really, but we usually go to about 2,000
Okay.
psi in the mold. So it kind of scales with area. In theory, we could make a large aerogel if we had a large enough hot press. But there's some issues with diffusion, and when you release all the supercritical gas. So we're working on that right now, working to scale up to 8x8 and 10x10 aerogels with
Inches.
10 by 10, yes, inches, with a 150-ton hot press.
So something like a
Yeah.
small window pane.
Yeah,
Kind of.
that's what we're going for.
And so are windows the thing you're particularly interested in seeing this be used for?
That's one of the things. I mean, we are focused on two things at this point. Mostly, one is the catalytic aerogels. The hot press doesn't necessarily provide any great advantage, except we can make them fast. Those are not monolithic. And then the other thing is the windows, which are monolithic, and that's where I think we have a great advantage.
So what are the catalytic aerogels interesting for?
They're interesting because we want to try. So what we're doing with them is we're playing around with different metals in the aerogels as a way of reducing the use of platinum, palladium, rhodium in a typical catalytic converter.
Okay.
So
like
if you
on
can
the
get-
exhaust of a car, for
Yeah,
example.
car exhaust. So that's our main application that we're looking at is three-way catalysts for use in automobile exhausts. And if you could, the aerogels give you a great surface area. So the idea is that enhanced surface area with a little bit of a metal, we're working with copper, cobalt, or some of the metals we've used, might be able to function as well as platinum or palladium.
So using low-cost metals in an aerogel to substitute for high-cost metals that we
Yes.
use today
Yes.
that are non-aerogel form.
Right.
Very cool. And so the hot press technology could be used to make that kind of stuff, which would be, I guess, a powder
Yes.
rapidly,
Yes.
or it can be used to make
make
monoliths for
monoliths,
something like
right.
aerogel windows.
Right.
Very
Right.
cool.
Right.
Okay, so can we actually go ahead and make some?
Yeah, they'll come on in and we'll put them on and process them.
Okay, great. So this is the hydraulic press you use to make monolithic aerogels.
Yes, and so what the students are doing right now is programming the press to take it through the 4 steps. And the 4 steps are seal, heat, release, and cool down. And you'll see what happens is the hot press platens provide the heating, and the sealing by applying a force, and the release by releasing the force. So he's checking the steps. We heat it to 550 Fahrenheit, hot presses in English units, and they're applying a force, in this case, of 50,000 pounds.
So what's inside the press?
So
That's
they
the
put
mold.
the mold in there. So what we do with the mold, it's an open bottom mold, and they lay it on the gasket material, which consists of graphite and then stainless steel. And we pre-compress that to get some sealing so that we don't end up with the material leaking out. So now Jacob is filling, there are empty wells in that mold, and he's filling each one up.
And that's the sol we just mixed in the vent hood before?
Yep.
And so the mold itself is made out of what?
The cold rolled steel for these, for the
Okay.
silica. When we do catalytic materials, we have to use stainless steel.
Cool.
Otherwise, we'll get a reaction.
And so when you say graphite and stainless steel gasket, those are like sheets underneath?
Yes, so it's a sheet of about 16th, or 32nd to 16th of an inch thick graphite, and the graphite provides a little bit of compliance to help seal, but it can take the high temperatures. More importantly, the stainless steel is there to keep the graphite from sticking to the mold.
Got it.
We've also used Kapton material. Stainless works well. Okay, so now that he's filled it, he's going to seal the top with that sheet of stainless steel foil and another piece of graphite. Then he'll close up the safety shield on the press. And he's going to close the flaps. Now you'll see the bottom flatten will start to rise up.
Cool.
So that'll rise. You can hear some noise in a minute when the pump kicks in.
How many times have you done this?
This is my second.
Second time?
Yep.
Oh, wow. Hopefully you don't screw it up. So what are we hearing?
That's the hydraulic, the pump on the press is pumping up. We're right now, it's 42,000 pounds, 45. It's going to pump it all the way up. The hydraulics up to 50,000 pounds.
So how many times tire pressure is that?
So the pressure in there, you got me. The pressure in the line is about 2,000 psi.
2,000
right?
psi,
So
okay.
what's that, like
400.
8 times what a tire pressure would
Oh,
be,
okay.
right?
I guess it depends on
Right?
so if your bike tire or car
Oh,
tire.
sorry. I was
Yes.
thinking of the car tire. Yeah. So once it gets there, it's fairly stable. It'll get quiet because the system's contained. Every once in a while, it has to do a little pump to get it back to 50, but right now it's going up to 50.
Cool.
Sealing that. And
So
then
this
the next
is-
step is it's going to start heating.
Okay, so
Seal.
the sealing phase is going on right now, and then it's
Yes.
going to start the heating phase.
Exactly.
Okay.
Exactly.
And so what
So now
temperatures?
it's heating. This next step.
You said
Yeah.
550 degrees
550.
Fahrenheit?
Yep.
Okay.
Yep.
It's about 200,
260,
260 degrees
yeah,
Celsius.
yeah,
Okay.
yep. The hot press is manufactured in the United States, so everything is in English units.
And how long does the sealing phase take, and how long does the heating phase
The
take?
sealing phase takes just 30 seconds.
Okay, so
and
it's-
then the heating, we're going to heat to 550, and we're heating at a rate of 3 degrees per minute. So
Okay.
it's going to take 2.5, 3 hours to do that.
So why don't you just heat it up as fast as you can?
So we can heat faster, but what happens, we know because we once built an optical mold and we put in, we watch what happens. So you get a lot of convection occurring as it heats.
I see.
And it's gelling during that time, and it's aging and strengthening. So we give it a little time. We think it gels within the first 100 degrees.
Okay.
By 100 degrees, I mean, by getting to 200 degrees. And then it strengthens and ages a little bit, so we think that provides some help.
So in the first 100 degrees Celsius, it's already gelled.
Yep.
Gelled. Okay.
And then once it gets to that temperature, we sort of sit there for about half an hour and let things equilibrate, and then we start to release that force.
Cool.
So after it reaches 550, the press is going to lower the restraining force on the mold, and that's when we do the supercritical extraction. Then after that, the press will cool the system down back to room temperature so you can handle the mold.
So talk about that release in the supercritical extraction. What's actually happening inside that makes it supercritical extraction?
So while we're heating this up, we bring in the temperature of the wet gel up above 550 degrees C, or 550 degree F, 260 C, and the pressure is also rising during this time, probably up about 2,000 psi. So we're at above the supercritical point of methanol. Now we've got methanol and water in there, but just a little bit of water, mostly methanol. So we're well above that state, and when the press releases, it's no longer sealed, and the supercritical fluid will seep out through the sides of the mold.
So basically,
and up into the vent.
The leakiness of the mold when you release the pressure is what starts the supercritical extraction.
Yes, yes.
And you said these are pressures up to about 2,000 psi
Yes.
in there? So essentially the mold in the hot press is your supercritical dryer.
Exactly.
It's just made in 3 pieces instead of 1.
Right.
Very cool. So the next thing we'll see then will be that release in about 2 hours.
Yes.
Very good.
Okay, so we're at the end of the 3-hour heating phase, and the press is starting to release at this point. The force is being lowered, and the supercritical fluids are going to escape over a period of about 30 minutes. So we'll come back in 30 minutes and see what happens next.
So are we going to actually see the hydraulic press move?
No, doesn't do anything. Just releases the force a little bit, and because of that, the
So
gas
it moves like an imperceptible amount
Yes,
that's just enough
sure.
for it to leak out then.
Yes.
And then where do the vapors go when they're being supercritically extracted?
They go up the vent, and they're vented out.
And that doesn't, that can't light on fire? That's on explosion hazard?
So we've never had a problem with it. We don't worry about it because the amount of methanol gas released is very small. It's only the methanol that's in the wet gel. There's no additional methanol in there.
Okay, great. So we'll check back in about half an hour.
Yeah, sounds good.
So it's been 30 minutes, and we're going to begin the cool down phase. How does that work?
So what's happened now is we have a very hot aerogel in the
550 degrees F.
550 degrees. The supercritical gases have escaped, and what we need to do is cool it down. So the back of the press is hooked up to chilled water. The chilled water flows in between these 2 platens, essentially cooling down, flows out, and the much hotter water escapes through the vent there, and you can see the steam coming off because the press is still very hot.
Very cool. No pun intended. So the aerogel is actually in there. It's done. It's been made. Now we just got to cool it down, bring it to room temperature. So why can't we just open it up? Why do you have to cool it down at all?
Because we can't handle the mold right
It's just
now.
too hot.
It's just too hot.
Okay, got it. So will the aerogel crack if it's not cooled down slow enough?
So if we have too high a cooling rate, it could crack. And essentially, we don't actually even need the hot press at this point. We could actually take it out and let it cool in the environment, but it's too hot to handle. So
Okay.
we leave it in
Makes
there.
it easier.
We cool at a rate somewhere between 3 and 5 degrees Fahrenheit per minute, and that results in good aerosols.
Very interesting. So when will this be cool enough to handle?
So about another 2 hours or so.
Okay, great. We'll
Right.
check back then.
Yep, great. Okay, so the system's cooled down, and the students brought us over the mold. All we need to do is pop the aerogels out of the mold so we can take a closer look. Could you do the honors for us?
Sure. So what do I do exactly?
Just kind of put your thumbs on either side
Okay.
and push them out lightly. They should come right out.
Okay. So we'll give it a shot. There we go. Okay. I think that does it. So
these aerogels turned out great. You can see they're very translucent, and there's no cracks. They're ready
look
to go.
really good. Yeah. So this is the kind of thing you'd like to see in monolithic windows.
Exactly.
Very exciting. Well, I can't wait to see these scaled up into windows we can have in our houses one day.
Good.
I'm here with Luisa Posada. She's a senior undergraduate here at Union College majoring in chemistry, and she's worked on catalytic aerogels and is going to show us some pretty colorful looking aerogel materials she's worked on.
Yep, exactly. So right here, I have a couple of already made aerogels. This one is cobalt aluminum,
Oh.
and these are...
So the cobalt gives it that blue color.
Exactly.
Very nice.
And then here I have some interesting copper alumina, which are quite not as pretty as the cobalt. However, they have great catalytic abilities, which is what we're interested in.
So how do you make these kinds of materials? How are they different than silica aerogels?
So the method that we use is called the sol gel method, and we first start. There are several ways to make these aerogels. One is called the precursor, and the other one is called the impregnation method. What I've been using recently is the impregnation method, which you first start with a regular alumina gel, and then you impregnate that gel with a copper or any other metal solution. You let that sit, you let that gel, and then eventually you're gonna extract the solvent, and you're gonna leave out the aerogel. Other method that I've been doing recently with ceria is the precursor method, which is where you gel both the cerium and the alumina together, and then you extract the solvent after.
So when you're making alumina gels or Syria alumina gels, how do you do this? Are you using the epoxide-assisted method, or do you use alkoxides?
Yeah, I'm using the epoxide system. So we use propylene oxide as the protein scavenger to make the network, and then eventually we use our method to extract the solvent.
And then you use something like aluminum chloride and cerium chloride or cerium nitrate?
Right, exactly. We use just regular metal salts like aluminum chloride, cerium nitrate, stuff like that.
Very cool. And so do you find that propylene oxide goes bad on you all the time? Because that's what I always found. Is like it'll be good for a week and then all of a sudden it doesn't work anymore. Do you have that problem, or does
Actually, no.
Oh, yours behaves pretty well?
Yeah.
You must be better at keeping your reagents dry than me. So tell me a little bit more about the sol-gel chemistry going on in here. So you make your gels, and you said you've got the impregnation method where you soak the gel or in the metal salt and it kind of diffuses in.
Right.
And then you've got the co-gelation or the co-infiltration where you mix the two precursors together and get that gel. So how do you pick the metals that go into those gels? Why did you pick cobalt? Why did you pick aluminum?
Well, for the past years, a couple of students have been doing a lot of research regarding the catalytic abilities of those metals. I've recently chosen cerium oxide as a metal because we know that it has great oxygen storage abilities, it's great at going between the oxidation states, so it's good in terms of converting the gases inside the cars and stuff like that. So as of right now, we're just in the middle of making those aerogels and then eventually testing them to see if they're actually good at what we think they're good at.
Yeah, that's one thing that's really important with catalytic metals is that they have a number of different oxidation states that they can go into.
Right.
Very cool. Well, thank you very much, Louisa.
Yeah, of course, no problem.
So we have Adam Forty here, and he is an alumnus of the Aerogel Lab, but still a senior at Union College, majoring in mechanical engineering with minors in chemistry and philosophy.
Yeah.
And you're holding something very interesting here. Can you tell us what this is?
Yeah, so this is what's called corderite. It's actually what's already in catalytic converters in all kinds of cars and vehicles.
Cool.
And this one that you see here is completely uncoated. This is what you get out of the factory that produces it.
What's it made out of?
This is just a ceramic.
It's a ceramic,
It's
okay.
magnesium, aluminum, silica, oxides in there. So what we wanted to do is take what the chemists are doing in creating a perfect catalytic aerogel and put it in something that we can actually use. And that's find a way to apply your beautiful aerogel to this piece of material. That way we can actually put it in the car.
Got it.
So my main project when I was working with this in particular was trying different methods, because you can either make an aerogel, grind it up, get it wet, and then pour it on something like this and hope it sticks, which someone else had tried and didn't really work too well.
Okay.
Or try some other methods where we actually gel the aerogel on this material,
Okay.
and then hot press it with the whole extraction and everything, like as one piece.
So you put that with the wet gel into the hot press and then supercritically dry it in there and get the aerogel formed on the ceramic part.
Exactly.
Got
and more
it.
importantly than just on it, one of the things we were focusing on is getting it in it. You can't see it, but this material is extremely porous. That's probably that's a large part of why it's used.
So you can see these kind of channels that go through it if you
Yeah.
look at it the
Yeah.
right way, but you're saying that the walls of the material are also porous.
Exactly.
Okay.
The walls have lots of different tortuous pathways and everything through them that help when you put a catalytic material on it increase the effective surface area. So what we wanted to do is see how much aerogel can we put in those pores as well as on the surface that you see.
Cool.
And then we can hopefully use that to increase the catalytic activity that we're getting.
So what did you find in your research?
We found something that's actually really promising, though it seemed a little bit disappointing at first. Initially, nothing really stuck. And visibly, I would take out my samples, even after various methods were tried, from the hot press, and pieces of aerogel were there, and they would fall off or fall out of the channels. And then I did some SEM, so scanning electron microscopy images, some energy dispersive X-ray spectra as well to see what was stuck that we couldn't visibly see, and we saw an even but very faint distribution of our aerogel in there.
Okay.
So we realized there was something, not a lot. Okay, we'll catalytically test it anyway. And despite having, within significant figures, 0 grams, essentially, of our aerogel on the material, we were actually getting some catalytic activity.
So a little bit of aerogel goes a long way.
Yeah, we're not entirely sure how far we can take this, if this means that our catalytic test section was maybe doing some of the catalysis for us, or if there are other problems like the quarterite being overactive or something like that. But from what we saw, like, there's a chance that we don't need too much aerogel to really get a lot done.
Very exciting.
Yeah, it's really exciting.
Well, thanks a lot.
Yeah, no problem.
So this is Jeremy Manis. He's an undergraduate student in engineering here at Union College.
Yep.
And he's going to tell us a little bit about the catalytic aerogels that you're developing in the aerogel lab.
So my primary job in the lab is to basically run this system. I'm not actually responsible for making catalytic aerogels, but what this system does is test the performance of catalytic aerogels and see how well they basically catalyze pollutants that we run through. That kind of, if you can see the system, we have gas pollutants in these bottles.
So these are like simulated car exhausts.
Right, so this is simulated car exhaust. We have two different blends depending on the system we want to do. As you can see here, we have two different test chambers so that you can test two different samples. This system currently right here is set up just to test one sample at a time.
Okay.
And so what it does basically is the gas kind of flows through all these fancy plumbing and all these valves and up through the test section where the aerogel is actually located. And then we monitor what comes out through these gas analyzers, and we can tell how well the catalytic aerogels are performing.
Very cool. And so where does the aerogel actually go? How do you get it into this device?
So the aerogel actually just rests right in these test chambers. You can kind of, these are clamped on right now.
Do you unclamp them and
you
pour
can
it in or
unclamp
something?
them with just some wrenches and everything, and then you put about 20 milliliters of sample in there.
Okay.
And there's...
And that's like a powder that goes in?
Yeah, so
Okay.
usually we kind of crush it up and put it in there. Not really. We try to avoid having big chunks, but
Sure.
if that happens, it's all right.
Got it. And so this thing that the piping is in is a high temperature furnace?
Yeah. So this is what's in here. This is just an oven basically where
Okay.
we test at different temperatures to see how well they're performing as we heat up, as in like a typical exhaust system. So we start around 200 degrees Celsius and work our way all the way to 600 degrees Celsius.
Okay. And then what's the coil on the bottom for?
This right here?
Yeah.
This is just basically like a support system
Okay.
for these, for the plumbing.
Kind of like a spring.
Yeah.
Got
And
it.
so
Yeah.
if you can take a look down here, these two donuts right here are monitored by these syringe pumps, and
Okay.
that's just basically a humidity system that we implemented this past year. So we have a more accurate representation of like the exhaust system.
What's happening here? And have you seen good results? Do the aerogels break down car exhaust effectively?
So we do have some promising results. Right now we're kind of in a tricky situation with analyzing our results, but it does show that
It's
the
science.
aerogels are performing in a way that is beneficial.
Promising,
and,
yeah. So yeah, like it's a project. So
Right, exactly. It started in 2008 and
Still going on.
many
Yeah.
years to go.
Very exciting, very exciting. Very cool. I'm here with Sammy Kleinberg. He's an alumnus of Union College and the Aerogel Lab. He majored in chemistry and now has come back to work as a lab technician in the Aerogel Lab through a collaboration between Union College and a company called SunThru, LLC, which is working to commercialize aerogel windows with the hydraulic press technology. Sammy, thanks for talking with me. Could you tell me a little bit about what you did when you worked in the aerogel lab before and what you're doing now?
Will do. Steve, thanks for having me. I worked in the lab for my junior and senior year. I started out with the synthesis and characterization of catalytic aerogels, and then I moved to data collection and analysis with the UCAT, or Union College Aerogel Testbed. And then for my senior project, I tried to incorporate a gas chromatograph to probe the products of the catalytic reactions that happened in the testbed. As a lab tech, I've moved from the catalytic project to the Windows project. We're working on scaling up monolithic aerogel windows for industrial applications.
Very cool. So you have some aerogel windows here.
Yes, sir. Here we have some samples of not fully transparent, but transparent silica, fairly monolithic aerogels. What we're looking to do is scale this process up. This window is usable, but isn't all that practical for an industrial size window like the one that we have behind us. And so the project that I'm working on is collecting temperature and pressure data. We have what is here a 5.5 inch by 5.5 inch mold. We connect thermocouples 3 different places to monitor temperature during the process. And then we have a pressure transducer here that gets screwed into the mold. And this allows us to monitor temperature and pressure throughout the supercritical extraction process.
Very cool. And what have you found?
We found that in making a high-quality monolithic aerogel, that temperature and pressure at all points during the process are the most important factors in generating an aerogel that is monolithic in nature. So that's, you know, high quality, no cracks, something that a customer would be more than happy to, you know, to have on their building, to use in their building.
Could I take a look at some of these windows?
Yes, please, by all means.
So this one's interesting. It's got 4 segments, and we see here there's a pretty transparent, nice-looking segment, and then there's sort of decreasing clarity segments, and then the upper right-hand corner, this one's translucent. You can actually see through it if you look closely, so it's still transparent. These ones have some cracks. So what's the difference between among the different panels in this window?
So among the different panels, you have different precursors that are factored into the making of the actual aerogel.
Okay.
The aerogels that we saw being made earlier were made with TMOS. There are other precursors that are used that give rise to different properties, hydrophobicity being one of them. And these precursors, along with processing conditions, give rise to the different characteristics that we see in a finalized window product.
Cool. And now this one here looks very nice. All 4 segments look crack-free and pretty clear. I mean, I'd put windows like this in my house. I mean, I'm an aerogel guy, so maybe I'm biased. But you know, one thing I would note, though, is that, you know, although aerogel windows like these aren't perfect yet, you know, glass is early, as late as the 1950s, was still not that great. It was wavy, usually not in big pieces. It was only when the float glass process came out in the 50s and 60s that we started getting high-quality, large plate glass. So I think there's a lot of potential left, and it sounds like you're just now getting started in developing these windows.
Yes, we've moved up to a 10 by 10 square mold. We have another 8 by 8 that we've recently started experimenting with, and so the goal is to get a monolithic aerogel of this size that is of that quality, which has proven a bit difficult, but
I relate. Not always the easiest thing to do. Well, great. Thank you very much, Sammy. I really appreciate all the show and tell and the great work you're doing.
Thank you very much. I appreciate it.
One of the most exciting things happening here in the Union College lab, I've heard, is the commercialization of the technology you've developed for making monolithic aerogels to potentially fulfill the promise of silica aerogel windows. And so could you tell me a little bit about your company, SunThru, that you've started?
Sure. The roots of it go back to a program run by the National Science Foundation called Innovation Corps, or I-Corps, where they offer grants to researchers that they funded in the past to try to get them out of the lab. That's kind of their motto: get you out of the lab, talking to people, talking to potential customers who could use whatever it is you're doing in your lab. So we did that about 4 years ago, and through that process interviewed about 72 different people, showing them monolithic aerogels and trying to get at where could they use them. And from that, we came across the idea of using monolithic aerogels in fenestration or window applications.
So what are the value propositions of aerogels for windows?
Well, they're lightweight. They're highly translucent. Of course, they're not completely transparent. And they're very thermally insulating.
So this would help save energy in buildings and potentially...
Yes, so you could
still
cut
allow
down
light
on
to
the
come
energy
through.
loss, right, and allow light to come. People love windows. And so if you could get an aerogel in place of glass, you'd have a better product.
And the first sort of window application that we've been targeting is the daylighting market. And so daylighting windows are used in applications like an atrium or a school gymnasium where you have the windows high up. They don't have to be completely transparent as you'd want to have at home if you had a plate glass window, but they let light in. Those are also very big spaces to heat or to cool. So the heating and air conditioning costs associated with that energy could potentially be mitigated to some extent by using higher insulating windows. And so you see people going to double and triple pane windows. Triple pane windows, of course, are better than double pane windows, but they're a lot heavier. And the idea of putting a monolithic aerogel in between panes of glass would be higher insulating than just having air in a double pane window. And so we're looking at entering sort of the high performance window market, with the niche being probably going with some sort of daylighting, skylights or atrium lighting applications initially.
And unlike double pane and triple pane windows, aerogels are always good insulators.
That's right.
Yes.
But over time, double pane and triple pane windows lose their insulating value. Is that right?
Yes.
That's correct. And we've been able to make some monolithic aerogels that are, reasonable size. We're able to measure that they're highly thermally insulating. There isn't anything like this out on the market right now, and it's an exciting thing to bring something that you've developed in terms of research into the market. And it's something that's frankly just been an interesting thing for us to do. We're both, professors. We've been working, we do research, we like to talk about the research, but we do have this intellectual property that we've patented with the full support of Union College, and it seemed like if somebody was going to take this commercial, it was going to be us.
Yeah.
So you mentioned fenestration and daylighting, things like skylights and atriums. I know Cabot's using their Lumira aerogel products in daylighting applications with similar value propositions, energy efficiency, allowing light to transmit through. What's the advantage of using a monolith, which is harder to make than aerogel particles, over aerogel particles in daylighting applications?
So the granule applications are pretty opaque. You can get light through, but you can't see anything. So this offers an application where you get a lot more light through it. The other thing is that these, if we put a slight vacuum on them, are even more insulating than you would get out of a granular aerogel.
So it's the view and the potential better thermal
View.
insulation.
And the other, some of the granules, they tend to sag after time. So you fill a window with the granules, and after time, the granules will settle.
You have some gaps. We understand that that's probably not as big an issue with skylights, but it is a big issue with atrium kind of lighting, where the windows are mounted vertically.
Can you tell me a little bit about the process of going from the college to a company? So I understand a lot of the activities for SunThru are being done here at the college right now, but I imagine eventually this would spin out into its own building, its own staff, its own thing.
So at this point, we're more at the point of technology transfer, I'd say, where the sort of grants we've had from the National Science Foundation and from NYSERDA, the New York State Energy Research Development Authority, are to help us transition from the lab base to a technology that can be scaled up. So most of the research is done here at Union, but we have a partner who handles most of the business side of.
So the STTR grant from the National Science Foundation and the NYSERDA grant are both grants to SunThru, to the company, with subawards to Union College. And the Union College administration has been very supportive of us in this sort of effort. I mean, frankly, they paid for the patents, and if something comes of the patents, the college will benefit from that. And they also see the value of having students involved in the tech transfer enterprise as well.
Do you see your students coming through this lab potentially being the visionaries that help take SunThru to the next level?
It's a possibility. A lot of our students are headed straight for grad school or headed straight into industry, and as we grow SunThru, it may be that some of them head straight there. Some students are very entrepreneurial focused, and other students are more focused on the research aspect, so I think it really depends on the student. We did have a student involved in the I-Corps program that actually is a requirement, and we were either the first or second undergraduate institution to go through NSF's I-Corps program. You have to have a PI, and Anne was on sabbatical, so she was the PI for the I-Corps grant. You have to have what's called the entrepreneurial lead, and that's typically a graduate student or a postdoc, but of course we don't have graduate students or postdocs. So we had a student who had graduated off sequence. He finished at the end of the fall, and he wasn't going to be going to grad school until the following fall. And so the timing was right between the student being available and Anne being on sabbatical.
Mm-hmm.
It was the right time to do that. And I think anybody that has National Science Foundation research funding gets these emails from the National Science Foundation saying, wouldn't you like to try I-Corps? Wouldn't you like to try I-Corps? We'd been getting them for a while, and the timing was right to start that.
What are the milestones that you see for SunThru over the next 6 to 18 months and what do you see the long-term potential of SunThru being?
I think the immediate one right now is showing that with a more industrial scale hot press that we can actually fabricate larger monoliths.
How big do you want to make them?
We want to get to sort of the 10 by 10, 12 by 12, a window pane size is our sort of near-term goal. That's where we need to go with this.
Because we'd like to get a demonstration project going.
Right.
And there are certain places you can fund that. NYSERDA occasionally funds demonstration projects. So the idea, if we could get pieces that were 10 or 12 inches square, we could put them together into a piece that's big enough to install in a skylighting application or something and doing a demonstration.
In the long run, how big would you like to make aerogel monoliths?
5 feet by 9 feet, so they can go in like the big in
Skyscrapers.
skyscraper.
So that's the key size, 5 feet by 9 feet.
But that's not going to happen in 18 months.
No.
How long will it take for that to happen?
That's a good question. I mean, we have to do these scale-up experiments first, and you can't
Then we
just
can-
increase the size of everything and expect that it's all going to work the first time you try it. So
That's right.
there's
We
a
need to
certain
do the
amount of
first steps
research.
to be able to predict if we're going to be able to get to that size.
Can't build a race car before you
Right.
build a Model T.
Right.
And so cost is certainly something people think about. Windows are a pretty low-cost item in the grand scheme of things. Glass is pretty cheap, and window panes like double pane and triple pane windows are mature technologies, and so even if they're more expensive than regular windows, they're still cheap enough that they can be used in big construction. Aerogels, people often have the perception, are very expensive materials, and although that's changing and has been shown by many companies, it's no longer really the case. How do you address the price point issue with aerogel monoliths? What do you see these eventually costing, and how are they going to compete with other window technologies and other construction materials?
So I think they can, triple pane windows are not inexpensive. So I think that it's realistic that they could compete with the high-end kind of windows.
Okay.
We think what we have with our process really reduces manufacturing cost. And so that's sort of the model we're moving forward with. It much less time to make it and easier to make them. So we're hoping that reduces cost. We're sort of working with the number of, we want to get to like $10 per square foot if we can do it.
But we think we could enter the market at $20 per
Yeah,
square foot.
right.
How thick would you make panels that big?
Half inch.
A half inch.
Yeah.
Very cool. Well, Mary Ann, thank you very much for having me today and showing me the great things you're doing at Union College and with SunThru. And I look forward to having aerogel windows in my house made by you in the future.
Well, maybe you'll be our first customer.
I'll be happy to.
We'll talk to you about a demonstration project.
Thank
Yes.
you.
All right, thank you.
And Mary, thanks so much for having us. It was a really exciting tour, and it's great to see aerogel science in action.
Well, thanks very much, Stevie. It was great having you here. I know the students really enjoyed it as well. Thanks
Great.
very much for being with us.
For aerogel.org, I'm Steven Steiner, reminding you that aerogel's not just for NASA anymore. Log on and get involved. Thanks for watching.